Hello and welcome to Easy Sleep Science Channel. I'm so glad you're here with me tonight. This evening's journey will take us into the hearts of stars, the grand engines of the universe. Those burning spheres aren't just distant points of light in the sky. Some are so huge they could swallow our entire solar system. Others collapse into tiny remnants spinning hundreds of times per second. All of them are colossal forges creating the very elements that make up our bodies, our world, and everything we know. When you look up at the night sky, you are actually looking back in time. The starlight reaching your eyes tonight may have left its birthplace hundreds, thousands, or even millions of years ago. Some of those stars may already be gone, and what we see is only the whisper of what once was. But there are others that will keep shining long after our world fades away. If you enjoy these gentle journeys, please like, subscribe, or share your thoughts in the comments. They occur when a white dwarf in a binary system accumulates too much material from its companion, triggering a runaway thermonuclear blast. Because these explosions happen at nearly the same critical mass, their peak brightness is almost uniform across the universe. That makes them standard candles, reliable beacons for measuring cosmic distances. By comparing how bright they appear from Earth to how bright they truly are, scientists can calculate how far away they must be. Type Ia supernovae were pivotal in one of astronomy's greatest discoveries, the accelerating expansion of the universe driven by dark energy. They are not only spectacular endings, but also yardsticks that help us grasp the immensity of the cosmos. Supernovae spread heavy elements across the galaxy. Every atom of gold, silver, iron, and calcium on Earth was forged inside a star. When massive stars explode as supernovae, they launch those heavy elements into space, enriching the interstellar medium. Over time, that material becomes part of new stars, planets, and living things. Without supernovae, the universe would be far simpler. Mostly hydrogen and helium. Instead, each explosion seeds complexity. The iron in your blood and the calcium in your bones rode the shock waves of such blasts drifting through space before finding their way to Earth. Supernovae are violent endings but also beginnings, scattering the ingredients of life far and wide. In this way, stars are both creators and destroyers, ensuring the universe is not only full of light, but rich and diverse. You really are made of stardust. It sounds poetic, but it's a scientific fact. The atoms in your body were forged in stars. The oxygen you breathe, the carbon that builds your cells, the iron in your blood, all were created in stellar cores and in supernovae. Billions of years ago, long before Earth existed, those elements drifted through space, waiting for the chance to come together. Carl Sagan once said, "We are made of star stuff," a phrase that captures a profound truth. Every person, every tree, every rock is a collection of recycled stardust. When you look up at the night sky, you're not just seeing distant suns, you're looking at your own origin. Stars give us the raw materials. In turn, we are the universe becoming self-aware. The thread between us and the stars is direct, obvious, and humbling. Iron marks the threshold where fusion can no longer power a star. Stars shine by nuclear fusion, fusing lighter elements into heavier ones. This process releases energy, but only up to a point. When a star's core begins fusing silicon into iron, the balance changes. Iron does not release energy. When it fuses, it absorbs it. That means once iron builds up in the core, fusion can no longer counteract gravity. At that moment, collapse becomes inevitable, leading to catastrophic core implosion and usually a supernova. The presence of iron is a death sentence for massive stars, a marker that the fuel in a fundamental sense has run out. It's astonishing that a commonplace metal on Earth is the cosmic breaking point that decides when these giants of light will fall. Stars balance gravity against the outward pressure from fusion. A star exists thanks to a delicate equilibrium between two opposing forces. Gravity pulls all its mass inward, trying to crush it. Fusion, burning hydrogen into helium at the core, pushes outward with heat and radiation. As long as these forces balance, the star remains stable. Too much outward pressure and it expands. Too little and it contracts. Our sun has maintained this balance for billions of years and will continue to do so for billions more. But as core fuel runs low, the balance will tip and the sun will transform into something entirely different. This tug of war is the fundamental reason stars can exist as steady sources of light rather than collapsing instantly or blowing themselves apart. Without fusion, stars would collapse immediately. Fusion is not only what makes stars shine, it's what keeps them from falling inward. Without the outward push of fusion energy, gravity would crush a star into a compact, collapsed state in a flash. Even our gentle golden sun teeters on that razor's edge every second. The ongoing fusion of hydrogen into helium keeps it from collapsing under its own enormous weight. For larger stars, this balancing act is even more extreme, with stupendous forces constantly at odds. And when fusion finally ends, gravity wins, drawing the star down into a white dwarf neutron star, or black hole. Stars exist only as long as fusion continues. Their light is a fragile triumph over gravity's relentless inward pull. Not all stars are as patient as the sun. The most massive ones consume nuclear fuel at astonishing rates, up to 1 million times faster. That means despite being vastly larger and more powerful, they live extremely short lives, sometimes only a few million years. By contrast, the sun will shine for about 10 billion years. These fast-burning giants blaze blue, pour energy into space, and shape their galaxies with radiation and stellar winds. Their brief lives end violently, often in supernovae, that seed the universe with heavy elements. The contrast between them and sun-like stars shows how size dictates fate. The bigger the star, the shorter and more dramatic the life. They are cosmic fireworks, brilliant but fleeting. Smaller stars endure like candles across deep time, but the sun will swell into a red giant. Our sun, steady for now, has a dramatic future. In about 5 billion years, it will exhaust core hydrogen. As fusion shifts to helium, the internal balance changes, and the sun will expand into a red giant. Its surface will balloon outward, likely engulfing Mercury and Venus and possibly Earth. The outer layers will glow deep red, far cooler than today's golden light, while the core contracts and heats up. Eventually, those outer layers will drift into space as a glowing planetary nebula, and the core will collapse into a white dwarf. Though this transformation lies far ahead, it reminds us that even stars like the sun are temporary, following a path pre-written by the physics of fusion and gravity. Our familiar star will become something else entirely. On clear nights, Sirius rules the sky. Also called the dog star, it shines nearly twice as bright as the next brightest star, Canopus. Part of its prominence comes from its intrinsic luminosity. Another part is its proximity, just about 8.5 light-years, making it blaze in Earth's sky and often ending in supernova explosions. Their powerful light drives fierce stellar winds and surrounds them with glowing nebulae. These dazzling beacons remind us that a single star, for a brief moment, can dominate an entire region of the cosmos. Neutron stars are the remnants of such stellar deaths. When a massive star ends its life in a supernova, its core collapses into something extraordinary, a neutron star. Only about 20 kilometers wide, yet more massive than the Sun. Its matter is squeezed so tightly that protons and electrons merge into neutrons, forming the densest material known outside black holes. A single teaspoon of neutron star matter could weigh billions of tons. Their surfaces are solid, their gravity immense, and their magnetic fields beyond comprehension. Though small, they shine across the universe with beams of radiation or leftover heat. These ghosts of stars, the collapsed hearts of once great suns, spin rapidly, dense beyond imagining, and challenge everything we know about matter. Among neutron stars, some are even stranger. Pulsars spin at astonishing speeds, hundreds of rotations per second. Each turn sweeps a beam of radio waves or light across space, creating a rhythmic pulse as seen from Earth. The fastest millisecond pulsars can rotate over 700 times per second, faster than a blender blade. Their pulses are so precise that astronomers use them as cosmic clocks, even more accurate than atomic standards. When pulsars were first discovered in the 1960s, they were briefly suspected to be signals from alien civilizations until their true nature became clear. Today, they help test Einstein's theories and detect gravitational waves rippling across the universe, the most reliable lighthouses in the sky. Then there are magnetars stars, with magnetic fields so strong they can tear atoms apart. They are a special kind of neutron star, defined by the most intense magnetic forces in the cosmos, trillions of times stronger than Earth's. Such power can distort atomic structures, rip molecules apart, and reshape matter itself. When their magnetic fields suddenly shift, magnetars unleash bursts of energy, releasing in a fraction of a second as much power as the sun emits in hundreds of thousands of years. These eruptions can be seen across vast cosmic distances, briefly outshining the Milky Way. Fortunately, magnetars are extremely rare, and none lie close enough to threaten Earth. They are natural laboratories, showing what happens when physics is pushed beyond human limits. And not all stars are perfect spheres. When a star spins rapidly, centrifugal force makes its equator bulge, flattening it like a squashed ball. Achernar is a famous example, spinning so fast that its equatorial diameter is 50% larger than its poles. Such speed can fling gas outward, forming glowing disks around the star. It helps other restless souls find this peaceful place too. For now, there's nothing you need to do. Just sit back, slow your breathing, and let your mind soften. If you're ready, let's begin. The largest stars ever known could engulf Earth's orbit, a thought vast enough to make the imagination sway. The red supergiant UY Scuti has a radius over 1/700 times larger than our Sun. If placed at the center of the solar system, its surface would reach beyond Jupiter's orbit. Even smaller giants like Betelgeuse or VY Canis Majoris could easily envelop Earth's orbit. Such behemoths are rare because they burn their fuel quickly and live only a few million years a blink compared to the billions of years of more ordinary stars. Their swollen atmospheres are unstable, constantly shedding clouds of gas that drift through space like smoke. Their immense size reminds us that our sun, grand as it seems, is still a humble star among the titans scattered across the galaxy. These distorted stars shatter our idea of a perfect star and reveal a dynamic, restless reality where rotation matters as much as mass or age. At the extreme end are hypergiants, the most unstable and short-lived of all. They burn their fuel so violently that they shed their outer layers in massive stellar winds, losing an amount of mass equal to the sun's in just a few thousand years. Eta Carinae, the famous hypergiant, is surrounded by a giant nebula made from its own expelled material. Those storms of gas and dust enrich the galaxy, seeding new stars and planets. But for the star itself, it's a slow self-destruction, an almost certain path toward a supernova, and perhaps a black hole. They are cosmic firestorms, both beautiful and destructive, reaching the limits of what a star can become. When a star strays too close to a black hole, the ending is catastrophic. The black hole's gravity stretches the star like taffy. If it ventures too near, it's torn apart in what's called a tidal disruption. The star's matter swirls into a blazing disk, releasing light that can outshine an entire galaxy. Sometimes jets of matter are hurled out at nearly the speed of light, spreading across the universe. Though rare, these events let us see black holes that would otherwise be invisible, each one a cosmic tragedy of a radiant star devoured by gravity's hunger. When astronomers detect sudden flares from galactic centers, they may be witnessing such destruction. As the stars remain spiral inward, the disk heats to millions of degrees, glowing in X-rays and ultraviolet light. The glow can last for months or years before fading as the star disappears entirely. By studying them, we can measure black hole masses and understand how galaxies evolve, reminders that even the most enduring stars cannot escape the universe's deepest forces. When stars collide, they send ripples through the fabric of space-time itself. As two stars, especially neutron stars, spiral together, they release not only light, but also gravitational waves that stretch and squeeze space as they travel at light speed. In 2017, humanity detected such waves from a collision along with gamma rays and visible light, the first time we both saw and heard the same cosmic event. These mergers forge heavy elements like gold and platinum, spreading material that will one day form planets and life. Each gravitational wave is a message from distant stars meeting in unimaginable violence. Not all stars remain in their galaxies. Some are flung out at such high speeds that they escape entirely, drifting alone through the darkness between galaxies. These rogue stars may be ejected after close encounters with supermassive black holes or chaotic star clusters. Once exiled, they wander forever sometimes, with planets still orbiting them through endless solitude. Imagine a lonely sun traveling for billions of years far from home with no galaxy to call its own. Though hard to detect, astronomers believe countless such wanderers exist like embers scattered from a cosmic fire. In the early universe, before galaxies formed the first stars, the so-called population 3 stars were born. They were enormous, some hundreds of times more massive than the sun. With no heavy elements to cool their gas, they grew quickly and burned intensely, living just a few million years, a blink in cosmic time. When they died, they exploded in tremendous supernovae, spreading the first elements, carbon, oxygen, iron, the building blocks of planets and life. None of these primordial stars survives today. but their fingerprints remain in ancient chemical traces. By following those clues, scientists piece together the story of the first light, breaking the darkness, transforming the universe from pure hydrogen into a place capable of life. For stars like our sun, the final journey ends as white dwarfs and ultimately darkness. When they die, they shed their outer layers, leaving behind a hot, dense core called a white dwarf. At first, it glows brightly from leftover heat, but over billions, even trillions of years, it cools and fades into a black dwarf. None exist yet, because the universe is too young for even the oldest white dwarfs to have cooled that far. These black dwarfs belong to a future so distant, it's almost unimaginable, a silent monument to the fact that even the brightest stars eventually surrender to time. If the universe keeps expanding forever, that distant future will be a long drift into darkness. Stars will exhaust their fuel, new ones will cease to form, and galaxies will fade. Red dwarfs, the slowest burning of all, may glow for trillions of years, but even they will one day go out. The cosmos will cool, planets will freeze, and the sky will grow empty. In that heat, death, only black holes and faint embers of dead stars will remain. Though that future is unimaginably far, the thought feels both humbling and strangely peaceful. The story of the stars has a beginning and an end, and we exist in its bright middle. To look up tonight is to witness a universe still in its star-filled youth. And even if one day it all grows dark, some cosmological ideas suggest the story might not truly end. Perhaps the universe could bounce back or give birth to entirely new ones. In those fresh beginnings, the cycle of stars might ignite again. The elements forged in our cosmos could seed the next ensuring continuity through generations of universes. Just as dying stars enrich space for new stars to form, perhaps entire universes follow the same rhythm: collapse, rebirth, renewal. Though still speculative, such visions paint a picture where starlight never truly dies. It merely transforms, passing through ever grander scales of existence. In that vision, the stars above us aren't just part of our universe. They are notes in an endless symphony of light and rebirth. The smallest stars can shine for trillions of years. Not every star lives fast and dies young. The smallest stars, called red dwarfs, burn fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. Compared to the sun, they are dimmer and cooler, often invisible to the naked eye from Earth. Even so, they are the most common type of star in the universe, making up the majority of suns in the Milky Way. Because they live so long, red dwarfs may host planets where life has time to arise and evolve on scales beyond our imagination. No red dwarf has yet reached old age. The universe is still too young. That means the night sky in the far future will still be lit by these persistent red embers long after brighter stars like the sun have vanished. Over trillions of years, only faint red stars will remain. As the universe grows older, the brightest, most massive stars will go dark first. Blue giants and supergiants live only millions of years, while sun-like stars last billions. But red dwarf, small, thrifty stars endure for trillions of years. On such vast time scales, they will become the universe's dominant sources of light. Galaxies in the distant future may glow only with a dim red hue, giving us a gentler, more solitary sky. In the end, even these durable stars will run out of fuel, fade into white dwarfs, and ultimately become black dwarfs. The universe will shift from a radiant star-filled expanse to a realm of scattered embers cooling into darkness. It is a portrait of cosmic twilight, where the last stars burn, quietly guiding the universe into its final chapters. For now we live in a golden age, surrounded by countless suns of every size and color. Stars can orbit close to supermassive black holes. At the centers of galaxies lurk supermassive black holes weighing millions to billions of times the sun. Astonishingly, stars can orbit right near them, tracing paths that test the limits of gravity. In the Milky Way, astronomers have observed stars whipping around Sagittarius A, the black hole at our galaxy's core. A star like S2 sweeps past at a distance of just 17 light hours, as thin as a strand of hair in cosmological terms. At periapsis, it moves at over 5,000 kilometers. Tracking these orbits lets scientists measure the black hole's mass with extraordinary precision and verify Einstein's predictions about how gravity warps space-time. These stars survive where we'd expect them to be torn apart, showing that even in the shadow of a black hole, the dance of starlight can continue. The fastest stars can be slingshotted away from a black hole. When a star dives too close to a black hole, it isn't always destroyed. Sometimes it's flung out at tremendous speeds, accelerated by the extreme gravity. These hypervelocity stars can race at millions of kilometers per hour, fast enough to escape their home galaxy. The Milky Way hosts a few such runaways, now speeding into intergalactic space. Their journeys may begin near Sagittarius A, where interactions with the central black hole act like a gravitational slingshot. If any planets remain bound, the result is bizarre, a solar system hurled alone through cosmic darkness. And some stars shine so fiercely that they challenge the brightness of entire galaxies. While most stars glow with moderate light, a few rare ones, quasars or hyperluminous stars, release more energy than billions of suns combined. Eta Carinae. A luminous blue variable radiates with the brilliance of a small galaxy. In the 19th century, it erupted so violently that it became the second brightest star in the night sky. Even from over 7,000 light-years away, such stars live dangerously, devouring their fuel at terrifying. The smallest stars can shine for trillions of years. Not every star lives fast and dies young. The smallest stars, called red dwarfs, burn fuel so slowly that they can shine for trillions of years, far longer than the current age of the universe. Compared to the sun, they are dimmer and cooler, often invisible to the naked eye from Earth. Even so, they are the most common type of star in the universe, making up the majority of suns in the Milky Way. Finding these exiles among the stars reveals how dynamic galaxies really are, and that black holes don't just decide what falls in, they also decide what gets thrown out. Many of the stars you see are actually multiple star systems. To the naked eye, a star is often just a point of light. In reality, many are binaries, triples, or even larger groups bound by gravity. Binary systems are especially common with two suns orbiting a shared center of mass. Some pairs are close enough to exchange matter, others are so far apart that they take thousands of years to complete a single orbit. For an observer on a planet circling such a system, the sky might see 2 or 3 suns rise and set, casting overlapping shadows. A famous example is Alpha Centauri, our closest stellar neighbor, which is a triple system. By studying these pairs and groups, astronomers better understand how stars form and evolve. What looks like a solitary point of light is often a hidden family turning together in a long, graceful waltz. The death of one star can spark the birth of many others. When a massive star ends as a supernova, it doesn't simply vanish, it reshapes its surroundings. The explosion sends shock waves into nearby clouds of gas and dust, compressing them and triggering waves of new star formation. In this way, the death of one star can ignite the birth of many more. Our sun may have been born from such an event in a nebula enriched by heavy elements cast off by earlier giants. These cycles keep galaxies fertile with starlight, continually recycling matter into new forms. Each brilliant star leaves more than ashes. It leaves seeds for future suns, planets, and perhaps life. Stars don't simply end. They pass the torch, kindling the next chapters in the universe's unfolding story. A few stars explode multiple times in rare repeating supernovae. Although most stellar explosions are final, there are exceptions. In extremely rare cases, a massive star can erupt violently, survive, and then explode again years or decades later. These events are called pulsational pair instability supernovae. The star becomes unstable, ejects enormous amounts of mass, then temporarily stabilizes, only to later collapse for good. Such stars brighten erratically, producing multiple dazzling flares that can make astronomers think they're witnessing several supernovae in the same place. These unusual deaths reveal how diverse massive star fates can be and how much we still have to learn about the limits and instabilities of nuclear fusion. In a cosmic sense, these are stars that refuse to let go, leaving a dramatic, flickering record of their final struggle with gravity. Type Ia supernovae help us measure the size of the universe. Type Ia supernovae are a special class of stellar explosions that shine with remarkably consistent brightness. They occur when a white dwarf in a binary system accumulates too much material from its companion, triggering a runaway thermonuclear blast. Because these explosions happen at nearly the same critical mass, their peak brightness is almost uniform across the universe. That makes them standard candles, reliable beacons for measuring cosmic distances. By comparing how bright they appear from Earth to how bright they truly are, scientists can calculate how far away they must be. Type Ia supernovae were pivotal in one of astronomy's greatest discoveries, the accelerating expansion of the universe driven by dark energy. They are not only spectacular endings, but also yardsticks that help us grasp the immensity of the cosmos. Supernovae spread heavy elements across the galaxy. Every atom of gold, silver, iron, and calcium on Earth was forged inside a star. When massive stars explode as supernovae, they launch those heavy elements into space, enriching the interstellar medium. Over time, that material becomes part of new stars, planets, and living things. Without supernovae, the universe would be far simpler, mostly hydrogen and helium. Instead, each explosion seeds complexity. The iron in your blood and the calcium in your bones rode the shock waves of such blasts, drifting through space before finding their way to Earth. Supernovae are violent endings, but also beginnings, scattering the ingredients of life far and wide. In this way, stars are both creators and destroyers, ensuring the universe is not only full of light, but rich and diverse. You really are made of stardust. It sounds poetic, but it's a scientific fact. The atoms in your body were forged in stars. The oxygen you breathe, the carbon that builds your cells, the iron in your blood, all were created in stellar cores and in supernovae. Billions of years ago, long before Earth existed, those elements drifted through space waiting for the chance to come together. Carl Sagan once said, "We are made of star stuff," a phrase that captures a profound truth. Every person, every tree, every rock is a collection of recycled stardust. When you look up at the night sky, you're not just seeing distant suns, you're looking at your own origin. Stars give us the raw materials. In turn, we are the universe becoming self-aware. The thread between us and the stars is direct, obvious, and humbling. Iron marks the threshold where fusion can no longer power a star. Stars shine by nuclear fusion, fusing lighter elements into heavier ones. This process releases energy, but only up to a point. When a star's core begins fusing silicon into iron, the balance changes. Iron does not release energy. When it fuses, it absorbs it. That means once iron builds up in the core, fusion can no longer counteract gravity. At that moment, collapse becomes inevitable, leading to catastrophic core implosion and usually a supernova. The presence of iron is a death sentence for massive stars, a marker that the fuel in a fundamental sense has run out. It's astonishing that a commonplace metal on Earth is the cosmic breaking point that decides when these giants of light will fall. Stars balance gravity against the outward pressure from fusion. A star exists thanks to a delicate equilibrium between two opposing forces. Gravity pulls all its mass inward, trying to crush it. Fusion, burning hydrogen into helium at the core, pushes outward with heat and radiation. As long as these forces balance, the star remains stable. Too much outward pressure, and it expands. Too little, and it contracts. Our sun has maintained this balance for billions of years, and will continue to do so for billions more. But as core fuel runs low, the balance will tip, and the sun will transform into something entirely different. This tug of war is the fundamental reason stars can exist as steady sources of light rather than collapsing instantly or blowing themselves apart. Without fusion, stars would collapse immediately. Fusion is not only what makes stars shine, it's what keeps them from falling inward. Without the outward push of fusion energy, gravity would crush a star into a compact collapsed state in a flash. Even our gentle golden sun teeters on that razor's edge every second. The ongoing fusion of hydrogen into helium keeps it from collapsing under its own enormous weight. For larger stars, this balancing act is even more extreme, with stupendous forces constantly at odds. And when fusion finally ends, gravity wins, drawing the star down into a white dwarf neutron star or black hole. Stars exist only as long as fusion continues. Their light is a fragile triumph over gravity's relentless inward pull. Not all stars are as patient as the sun. The most massive ones consume nuclear fuel at astonishing rates, up to 1,000,000 times faster. That means, despite being vastly larger and more powerful, they live extremely short lives, sometimes only a few million years. By contrast, the sun will shine for about 10 billion years. These fast-burning giants blaze blue, pour energy into space, and shape their galaxies with radiation and stellar winds. Their brief lives end violently, often in supernovae that seed the universe with heavy elements. The contrast between them and sun-like stars shows how size dictates fate. The bigger the star, the shorter and more dramatic the life. They are cosmic fireworks, brilliant but fleeting. Smaller stars endure like candles across deep time, but the sun will swell into a red giant. Our sun, steady for now, has a dramatic future. In about 5 billion years, it will exhaust core hydrogen. As fusion shifts to helium, the internal balance changes and the sun will expand into a red giant. Its surface will balloon outward, likely engulfing Mercury and Venus, and possibly Earth. The outer layers will glow deep red, far cooler than today's golden light, while the core contracts and heats up. Eventually, those outer layers will drift into space as a glowing planetary nebula, and the core will collapse into a white dwarf. Though this transformation lies far ahead, it reminds us that even stars like the sun are temporary, following a path pre-written by the physics of fusion and gravity. Our familiar star will become something else entirely. On clear nights, Sirius rules the sky. Also called the dog star, it shines nearly twice as bright as the next brightest star, Canopus. Part of its prominence comes from its intrinsic luminosity. Another part is its proximity, just about 8.5 light years, making it blaze in Earth's sky. Because they live so long, red dwarfs may host planets where life has time to arise and evolve on scales beyond our imagination. No red dwarf has yet reached old age. The universe is still too young. That means the night sky in the far future will still be lit by these persistent red embers long after brighter stars like the sun have vanished. Over trillions of years, only faint red stars will remain. As the universe grows older, the brightest, most massive stars will go dark first. Blue giants and supergiants live only millions of years, while sun-like stars last billions. But red dwarfs, small, thrifty stars, endure for trillions of years. On such vast timescales, they will become the universe's dominant sources of light. Galaxies in the distant future may glow only with a dim red hue, giving us a gentler, more solitary sky. In the end, even these durable stars will run out of fuel, fade into white dwarfs, and ultimately become black dwarfs. For thousands of years, ancient cultures have paid attention to Sirius, tying it to myth-farming calendars and navigation. In ancient Egypt, the rising of Sirius at dawn signaled the Nile's flood season. Today, astronomers know Sirius is actually a binary system. Sirius A, a white, hot, and bright star, and Sirius B, a faint but dense white dwarf that was once a large star. To the naked eye, they merge into a single razor-sharp point of light. Sirius isn't just dazzling, it reminds us that what we see in the night sky often hides deeper stories. Long before telescopes, people named the brightest stars they could see. Those names carried meanings linked to agriculture, seafaring, or legend. Stars like Betelgeuse, Rigel, and Aldebaran have names rooted in Arabic tradition, while Vega and Altair come from ancient Arabic and Latin roots. In China, India, Greece, and Egypt, stars were woven into stories that helped civilizations make sense of the sky. To this day, those ancient names endure, connecting us to people who looked up at the same sky millennia ago. Behind every familiar constellation is a tapestry of human history, with names passed down through language and culture. Even though astronomers use catalog numbers for precise measurements, the old names still echo across time. They remind us that our bond with the stars is not only scientific, it is cultural, stretching back to the dawn of civilization. Long before compasses and GPS, the stars were reliable guides. Polynesian navigators crossed the Pacific by memorizing star risings and settings, steering outrigger canoes across thousands of kilometers of open ocean. The North Star, nearly fixed in the sky, has long been used in the Northern Hemisphere to determine latitude. Arab merchants, Greek sailors, and Viking explorers all relied on the map of the sky to find their way. Even seasonal migrations of people and animals were often timed by the stars. These skills were passed down orally through songs and stories. They encoded an entire star map. Celestial navigation demanded extraordinary memory and keen observation, but it worked. Long before technology, humans trusted starlight to reach safe new shores. Today, those same stars still shine above. We just gaze at them with wonder, more than out of necessity. Polaris is famous as the North Star, a point that appears almost still while other stars wheel around it. But it hasn't always held that role, and it won't forever. Earth's axis wobbles slowly over a roughly 26,000-year cycle called precession. That causes the pole star to change over time. Around 3000 BCE, Thuban in Draco marked true north. About 12,000 years from now, the bright star Vega will take its place. Polaris is merely the current chapter in a long story of a changing sky. Ancient works from certain pyramids to stone circles are aligned to stars that once wore the northern crown. Tracking the pole star's changes is like watching Earth breathe across millennia, a reminder that even the patterns we trust are always in motion, and our sky would look different from other worlds. If you could stand on a distant planet, the familiar constellations would vanish. From Earth, stars seem to group only because of our angle of view. Seen from many light years away, their arrangement would distort into unfamiliar shapes. On a planet orbiting Proxima Centauri, our sun would be just a dim extra star in the sky. From the Andromeda galaxy, the Milky Way would appear as a bright glowing band, while our familiar stars would blend into that spiral. This change in perspective shows that constellations are an illusion of distance and viewpoint. The night sky isn't a fixed painting, but a three-dimensional ocean of suns appearing different from every observing shore. Imagining other skies helps us realize how deeply our view of the universe is shaped by where we stand within it. The constellations we know, Orion, Cassiopeia, the Big Dipper, are only temporary. Over thousands and millions of years, stars drift and shift relative to one another. Gradually, those familiar figures will deform beyond recognition. The hunter Orion may lose his belt. The Big Dipper may no longer look like a ladle, and new star patterns will appear. For us, the changes are too slow to notice within a lifetime, but on cosmic timescales, the sky is always changing. Future civilizations, even future life forms, will inherit skies with different maps. Their constellation myths will carry the flavor of their era, just as ours are tied to the ancients. The constellations we see tonight are only a snapshot of a fleeting arrangement, a reminder that nothing is permanent, not even the outlines we draw on the heavens. Gravity bends light, a prediction of Einstein confirmed a century ago. When light from a very distant star passes near a massive object like a galaxy or a black hole, it can be bent and magnified, the phenomenon of gravitational lensing. Sometimes it splits a star's light into multiple images, or makes it appear far brighter than it truly is. Astronomers have even observed individual stars magnified this way briefly. Flaring into view across billions of light-year stars we could never see without nature's magnifying glass. This shows that space isn't empty. It's elastic bending light to reveal hidden treasures. Even a star's path is shaped by gravity's invisible hand. And constellations' cultural sketches on the sky are not eternal either. As the Milky Way turns and stars drift, some of today's famous shapes will dissolve. In about 50,000 years, Orion will lose its familiar form. A few million years from now, the Big Dipper may no longer resemble a ladle. To future observers, those constellations might be unrecognizable. Just as the ancients saw a different sky than we do, our descendants will have skies of their own. The constellations we know are only temporary arrangements. Our myths are tied to a pattern passing through. The sky has a history, and the maps we draw will one day be as old as antique sea charts. Though they seem still, stars are always moving. Distances so vast make their motion nearly invisible to the eye. But over centuries and millennia, changes add up. That slow drift is called proper motion. Barnard's star, for example, shifts noticeably against the background in just a few decades, the fastest proper motion of any star in the sky. Comparing ancient star maps with modern ones reveals the sky's slow shuffle. Even the shapes of constellations have changed slightly over human history. What seems eternal is not. Stars aren't painted on a dome, they are suns traveling through the galaxy, each with its own path and story. Their light traces lines of motion across cosmic time. Our sun doesn't stand still either. It orbits the Milky Way's center roughly every 200 million years. Along the way, its neighborhood changes. Stars near us today will drift away, making room for others to pass through our galactic street. In the distant past, the sun's closest neighbors were entirely different. Their light once blended into our sky in another arrangement. As the journey continues, the constellations around us will distort, and familiar stars will fade from view. This cosmic motion shows that even the sun's position is only temporary part of a grand rotation carrying us around the galaxy. To look at the sky is to see a single frame of an endless voyage where the sun's companions come and go through the ages. And at the outskirts of galaxies, glittering globular clusters hold some of the oldest stars in the universe. Globular clusters are dense, spherical swarms, often containing hundreds of thousands of stars packed into a relatively small space. They orbit the outskirts like sparkling satellites, each cluster a fossil from the early universe. Many in the Milky Way are over 12 billion years old, nearly as ancient as the universe itself. Their stars are typically faint red dwarfs and long-lived giants, the massive ones burned out long ago. Through a telescope, a globular cluster looks like a blinding snowball, stars so crowded that the core blurs into a haze. But they're more than beautiful. They are windows into the past, showing how the first stars formed and lived. Studying them is like reading a chronicle written in starlight, tracing the Milky Way's earliest days. Hidden among generations of younger stars are elders' suns, almost from the dawn of time. Some are over 13 billion years old, nearly as old as the universe. They formed from primordial gas containing very few heavy elements. Astronomers identify them by studying spectra, the fingerprints of elements in starlight, and finding signatures largely untouched since the Big Bang. Such ancient stars are rare, but they offer clues to the first moments of star formation before galaxies matured and heavy elements enriched the cosmos. To see one is to touch deep time, connecting with a survivor from when the universe was young and dark, when the sky had only begun to sparkle with its first stars. Stars can outlive the galaxies that gave birth to them. Galaxies are dynamic systems, sometimes colliding, merging, or being torn apart by gravity. But the stars within can outlast all that turmoil. A star born in a small galaxy might be swept into a larger one after a merger continuing to shine for billions of years. The universe will shift from a radiant star-filled expanse to a realm of scattered embers cooling into darkness. It is a portrait of cosmic twilight, where the last stars burn quietly, guiding the universe into its final chapters. For now, we live in a golden age, surrounded by countless suns of every size and color. Stars can orbit close to supermassive black holes. At the centers of galaxies lurk supermassive black holes weighing millions to billions of times the sun. Astonishingly, stars can orbit right near them, tracing paths that test the limits of gravity. In the Milky Way, astronomers have observed stars whipping around Sagittarius A, the black hole at our galaxy's core. A star like S2 sweeps past at a distance of just 17 light hours, as thin as a strand of hair in cosmological terms. At periapsis, it moves at over 5,000 kilometers. Some are even flung into intergalactic space, wandering alone long after their home has vanished. In this way, stars can survive events that erase the very structures that formed them. It reminds us that stars are both products of galaxies and independent actors, persisting even as galactic boundaries change. Those solitary survivors are cosmic witnesses, living through upheavals on scales almost beyond imagination. Their light endures longer than the cradles that first kindled them. Not every star shines in solitude. Somewhere, strange shells of gas and dust expelled from their surfaces during unstable phases. These shells can form rings, arcs, or bubbles that glow under the star's radiation. The reasons vary. Some stars lose mass through powerful stellar winds. Others undergo outbursts that puff up their outer layers and cast them off in an instant. Often, that material merges into complex nebulae, creating patterns both beautiful and puzzling. Sometimes astronomers see multiple shells, hinting the star has molted several times. These gaseous veils aren't mere ornament, they enrich the galaxy with elements that will one day build new stars and planets. Studying them is catching a star mid-transformation, wearing its history in luminous mist. Wolf-Rayet stars are rare, massive, and wildly unstable. They are so hot and bright that their outer layers are stripped away by ferocious stellar winds. These winds can blow off more than 10 Earth masses of material each year, creating spectacular halos of gas and dust around the star. Their exposed cores blaze often above 50,000 degrees. Wolf-Rayet stars are seen as a brief, violent transitional phase before a supernova or a collapse into a black hole. Though rare, they play an outsized role in enriching galaxies with heavy elements. Their chaotic winds and explosive ends scatter raw ingredients for new worlds. They are stars living on the edge, burning too fiercely to last radiant before the inevitable finale. And when a star races through space at high speed, it can plow into surrounding gas and dust, forming a bow-shaped shockwave ahead, like the wave at a ship's prow. These bow shocks glow in infrared, where astronomers see them as arcs or crescents in front of the star. They reveal both the star's motion and the density of the medium it traverses. Such stars are often runaways kicked from their birthplaces by supernova blasts or gravitational encounters. Their glowing trails are fleeting, present only while the star crosses a gas-rich region. Each bow shock is like a wave frozen in space, a luminous footprint marking a star's restless journey through the galaxy. Not every star stays bound to where it was born. Some are ejected from clusters or even from galaxies at speeds of hundreds of km, so it says. Runaway stars can be launched by a supernova's kick or close encounters with supermassive black holes. In extreme cases, they reach hypervelocity fast enough to escape an entire galaxy. For any planets orbiting such a star, the outcome is extraordinary. An entire solar system hurled alone into the cosmic wilderness. Though rare runaway stars reveal the universe's chaotic side, where a star's life can be uprooted suddenly by violent forces. They slash bright paths across a galaxy like exiles, reminding us that even stars aren't immune to gravity's unpredictable games. And newborn stars rarely show themselves right away. They're born inside thick clouds of gas and dust, leftovers of the material that collapsed to form them. These dusty cocoons block visible light, hiding stars from ordinary telescopes. Instead, astronomers use infrared and radio waves to pierce the veil, revealing clusters of protostars still gathering mass. Young stars are often surrounded by disks of material places where planets may later form. Over time, radiation and stellar winds clear the dust. The stars emerge and they shine freely. To glimpse a newborn star is to witness creation in progress, a rare, fragile phase that occupies only a tiny fraction of a star's life. And a star doesn't begin its life by burning nuclear fuel right away. Before that moment, it exists as a protostar, a dense clump of gas collapsing under gravity. As it contracts, the core heats up, and the protostar glows faintly from gravitational energy alone. During this stage, which can last hundreds of thousands of years, the star draws in material from its surroundings, growing larger and heavier. Jets of gas often shoot from its two poles, marking its presence amid the dark clouds where it formed. Only when the core temperature reaches about 10 million degrees do hydrogen fusion reactions begin, and the protostar officially becomes a star. That hidden stage is a quiet prelude to starlight, when the future of a sun is being assembled from the dark. But not every object fits neatly into star or planet. Brown dwarfs sit in the twilight zone between the too massive to be called planets, but not massive enough to sustain stable hydrogen fusion like true stars. They glow faintly from the leftover heat of formation. Some can fuse deuterium-heavy hydrogen briefly before fading into cool, dim objects. Brown dwarfs are hard to detect, shining mostly in infrared. Even so, astronomers have found many of these in-betweeners drifting alone or orbiting stars. They show that the universe manufactures objects so diverse they challenge our categories. In one sense, they are failed stars or oversized planets, reminders that the cosmos rarely obeys simple definitions. Stars aren't always solitary. When two orbits are close enough, they can spiral together and merge. Such collisions release enormous energy, sometimes producing spectacular outbursts visible across a galaxy. After merging, the new star is often larger, hotter, and more unstable, with surges of fusion in its core. Some mergers can create rare types of stars that are hard to form, otherwise like blue stragglers. which look rejuvenated thanks to the merger's infusion. These events can also leave behind disks of material that might shape new planets or simply disperse into space. Violent yet common stellar mergers are part of the cosmic cycle, reshaping stars into new forms and reminding us that stellar lives are interwoven, governed by neighbors and chance encounters. In many binaries, one star grows at the expense of its companion. As it ages and swells into a red giant, its outer layers can spill onto the other star under gravity's pull. This mass transfer can completely change both stars' destinies. The recipient can become hotter and brighter while the giver is stripped down to its core, sometimes left as a white dwarf. In extreme cases, the stolen mass can push a star over a stability threshold, triggering a nova or even a supernova. These interactions produce some of the sky's most dramatic phenomena, from flickering variables to violent explosions. Binaries are the cosmos's thieves and victims, their lives bound in relationships as complex and gripping as myth, only played out in light and fire over millions of years. Not just pairs, some trios are bound in subtle gravitational dances. Triple star systems can be arranged in many ways, two stars close together with a third circling farther out, or all three locked in evolving complex patterns. These systems can induce chaotic gravitational effects, influencing the motion of any planets that orbit them. In some cases, planets end up on oddly tilted, eccentric orbits, experiencing multiple sunrises and sunsets. Triples are fairly common, showing the universe's taste for variety. Seeing one through a telescope is catching a glimpse of a foreign solar system utterly unlike our own, where day and night follow rhythms nothing like Earth's. Such stars remind us that our familiar solar system is only one possibility among countless strange arrangements in the cosmos. And science fiction isn't just fantasy. Planets really can orbit multiple stars at once. A planet can encircle a pair of stars on a stable path, experiencing twin sunsets and shifting light patterns. Other worlds orbit just one star in a pair, with the second rising and setting like an unusually bright moon. NASA has discovered several circumbinary planets with the Kepler telescope, proving these bizarre setups exist. Life under multiple suns would feel entirely different from Earth seasons. Illumination, even shadows, could behave in surprising ways. Stars aren't spread evenly across a galaxy. Many are born in giant batches. Star clusters can pack hundreds of thousands of suns into a relatively small volume of space. In dense globular clusters, centers can be so crowded that stars lie only fractions of a light year apart. In such environments, stars frequently interact, swapping companions or disturbing planetary systems. Open clusters, looser and younger, often blaze with hot blue, short-lived stars, whose brief lives highlight the group's youth. Looking at a cluster through a telescope is seeing an entire community of suns shining together, a reminder that many stars don't begin in solitude, but in crowded nurseries. Over time, clusters disperse their members, leaving the nest and drifting into the wider galaxy. Tracking these orbits lets scientists measure the black hole's mass with extraordinary precision and verify Einstein's predictions about how gravity warps space-time. These stars survive where we'd expect them to be torn apart, showing that even in the shadow of a black hole, the dance of starlight can continue. The fastest stars can be slingshotted away from a black hole. When a star dives too close to a black hole, it isn't always destroyed. Sometimes it's flung out at tremendous speeds, accelerated by the extreme gravity. These hypervelocity stars can race at millions of kilometers per hour, fast enough to escape their home galaxy. The Milky Way hosts a few such runaways, now speeding into intergalactic space. Their journeys may begin near Sagittarius A, where interactions with the central black hole act like a gravitational slingshot. If any planets remain bound, the result is bizarre, a solar system hurled alone through cosmic darkness. Unlike open clusters, which fade in a few 100 million years, globulars are far more enduring. Many are over 10 billion years old, nearly as ancient as the Milky Way itself. Their longevity comes from their dense structure, gravity binding hundreds of thousands of stars together. Across the ages, the brightest stars die off, leaving red giants and compact remnants, while dim red dwarfs continue to glow. These clusters orbit the galaxy like relics, survivors from when the Milky Way was still taking shape. Studying them reveals the early conditions of galaxy building and the chemical makeup of ancient stars. They're cosmic time capsules preserving information from an era long past. To gaze at a globular cluster is to look back through the universe's history. By contrast, open clusters are fragile relatives. They form as groups of a few dozen to a few thousand young stars, often inside sprawling stellar nurseries. Over hundreds of millions of years, the galaxy's tidal pull gradually tears them apart. Eventually, the stars disperse into the galactic disk, joining the general population. Our Sun is thought to have been born in an open cluster about 4.5 billion years ago, one that has long since dissolved. Temporary though they are, open clusters give us a snapshot of stellar youth where hefty hot blue stars light up surrounding gas in vivid colors. They show that stars aren't born alone, but as siblings, companions for a while before fanning out across the galaxy to live separate fates. And while galaxies like the Milky Way form stars at a steady pace, some galaxies enter frenzied birth spurts called starbursts. Their stars are born up to thousands of times faster than normal. Entire regions blaze with newborn clusters, their combined light like cosmic fireworks. Starbursts can be triggered by galaxy collisions when tidal forces compress immense reservoirs of gas into new stars. Spectacular as they are, these phases are brief on cosmic timescales, lasting only tens of millions of years. In the end, the galaxy's gas runs low and the boom quiets down. Such galaxies show how the universe's rhythms can swing wildly, sometimes calm, sometimes explosive, but always creative. They remind us that galaxies aren't static collections of stars, but evolving dynamic systems. Stellar nurseries can stretch for hundreds of light years. Stars are born in giant molecular clouds, vast reservoirs of gas and dust that can span hundreds of light years. Within them, gravity slowly gathers material into dense clumps that collapse into protostars. Telescopes reveal these nurseries as glowing nebulae places where young stars burn against the clouds that birthed them. The Orion Nebula, visible to the naked eye, is a nearby example full of hot blue stars, illuminating the region around them. Inside such nurseries, entire generations of stars can form together, creating clusters that later drift apart. To peer into a stellar nursery is to watch creation at work. The universe's raw ingredients are assembling into suns that may one day light planets and perhaps life. These clouds are the cosmos's wombs shaping the future skies of galaxies. Young stars often fire jets of material into space. As newborn stars grow from collapsing gas, many launch narrow streams of matter from their poles. These jets can extend for light years, plowing through the surrounding cloud and carving glowing streaks. The process likely helps regulate how the star gathers mass, venting energy outward while the remaining gas falls inward. In powerful telescopes, these jets appear as thin, luminous threads of red and blue, lit by shock waves where they strike nearby gas. Called Herbig-Haro objects, they're among astronomy's most beautiful sights, vivid markers of stellar adolescence. Though they last only tens of thousands of years, they record the full drama of star birth, a brief yet extraordinary stage before a star settles into its long, steady life. Some stars beat in brightness like cosmic heartbeats. Certain stars don't shine steadily. They pulse, brightening and dimming in cycles as they expand and contract due to changes in pressure and temperature in their outer layers. Some, like Cepheid variables, are so regular they serve as cosmic clocks with periods directly tied to their intrinsic brightness. By measuring their pulse, astronomers can determine their true luminosity and use them as distance markers across the universe. Others, like RR Lyrae stars, pulse faster but play a similar role in mapping the Milky Way. To the naked eye, they may twinkle oddly. Under close study, their heartbeats are revealed. Those steady rhythms carry across space, turning stars into natural timers that help us measure the universe's vastness. White stars are hotter than a blue flame. We often think fire is the hottest thing we know, but stars far outstrip even our hottest flames. White stars like Sirius A radiate at 10,000 degrees or more, far hotter than a blue gas flame on Earth. Their surfaces blaze so intensely that they emit light across a broad spectrum, appearing to our eyes as dazzling white or white-blue. These stars are typically more massive and younger than the Sun, consuming hydrogen more quickly. Their brilliance makes them easy to spot in the night sky, but their lifespans are significantly shorter than those of cooler stars. When you see a white star shining down, you're witnessing energy on a scale far beyond earthly fire, a nuclear furnace so hot that the word flame feels small by comparison. Red supergiants are among the coolest stars, yet the largest. Despite their ruddy glow, red supergiants are surprisingly cool by stellar standards. Their surface temperatures can be only about 3,000 degrees Celsius cooler than the Sun's roughly 6,000 degrees Celsius. But what they lack in temperature, they make up for in size. Stars like Betelgeuse swell to hundreds, even more than 1,000 times the Sun's radius, their vast atmospheres billowing into space. If Betelgeuse sat at the center of the solar system, it would reach beyond Mars's orbit. These are stars in their final acts, swollen giants on the verge of an inevitable supernova. Their red light in our sky is a sign of both grandeur and fragility. Though their surfaces are cooler, their interiors burn furiously, setting the stage for some of the most spectacular stellar explosions in the universe. Yellow stars like the Sun are actually quite ordinary. To us, the Sun is central and unique, but on the cosmic scale, it's the definition of average. Classified as a G-type main sequence yellow dwarf, it burns steadily, neither too massive nor too dim. Billions of sun-like stars are scattered across the Milky Way, each potentially hosting planets. The Sun's ordinariness is a gift big enough to sustain fusion for billions of years, but not so big that it dies too soon. It offers a stable, long-lasting home for life to arise and evolve. When you look up at the sky, it's comforting to know the Sun isn't unusual. If life exists elsewhere, it very likely orbits a star, just like this, golden, steady, reliable. Here, ordinary is precisely what's extraordinary. The most common type of star in the universe is the red dwarf. Though dim and hard to see with the naked eye, red dwarfs are overwhelmingly prevalent. Small, cool, and thrifty, they may make up as much as 3/4 of all stars in the Milky Way. Because of their faint red light, none can be seen from Earth without a telescope, even though they are incredibly abundant. By burning hydrogen very slowly, red dwarfs live for trillions of years, far longer than the universe's current age. That longevity makes them enticing candidates for habitable worlds because planets around them have ample time for life to develop. They are the universe's quiet workhorses, outnumbering the flashy blue giants that catch the eye. The galaxy's sparkling fabric is largely woven from these small, persistent suns. The rarest are the most massive blue giants. At the opposite end of the scale from red dwarfs are the blue giant stars, tens of times the sun's mass. They burn so fiercely that their lives last only a few million years, a blink by cosmic standards, and that brevity makes them rare. Even if many are born, they also die very quickly, leaving only a handful scattered through a galaxy at any given time. While alive, they blaze with astonishing brilliance, often visible across vast distances. Their ultraviolet radiation shapes whole regions of space, ionizing gas clouds and carving out bubbles in the interstellar medium. These stars are the fireworks of the universe, spectacular, brief, and impossible to ignore. To catch a blue giant is to witness a fleeting rarity, a titan on the verge of a dramatic, almost unimaginable death. Stars have colors that the human eye can barely perceive. Stars aren't only white or yellow. Their light spans the spectrum from deep red to icy blue, depending on surface temperature. Some shades are so subtle that human vision struggles to register them. To us, they may all look roughly white or bluish, but through scientific instruments, their colors stand out clearly. Ultraviolet bright stars pour out energy beyond our vision, while cooler stars glow in infrared, invisible without specialized sensors. Astronomers measure color with spectroscopy, splitting starlight into a rainbow to reveal temperature, composition, and motion. Finding these exiles among the stars reveals how dynamic galaxies really are, and that black holes don't just decide what falls in, they also decide what gets thrown out. Many of the stars you see are actually multiple star systems. To the naked eye, a star is often just a point of light. In reality, many are binaries, triples, or even larger groups bound by gravity. Binary systems are especially common with two suns orbiting a shared center of mass. Some pairs are close enough to exchange matter. Others are so far apart that they take thousands of years to complete a single orbit. For an observer on a planet circling such a system, the sky might see 2 or 3 suns rise and set, casting overlapping shadows. A famous example is Alpha Centauri, our closest stellar neighbor, which is a triple system. By studying these pairs and groups, astronomers better understand how stars form and evolve. In truth, the night sky is more colorful than we think, painted with hues beyond human eyesight. What we see is just a glimpse of a far richer palette, blazing across the universe in every kind of light. A star's color reveals its temperature. Color isn't mere ornament, it's a thermometer for stars. The bluer the star, the hotter it is. Blue giants can burn at tens of thousands of degrees. Red dwarfs at only a few thousand. Yellow stars like the sun sit in between. This relationship, Wien's law, lets us estimate stellar temperatures simply by studying their light. Telescopes equipped with filters can measure color balance, yielding highly precise results. Spectra also reveal a star's composition, motion, and age. Every star is a story written in color, a direct translation from temperature to hue. Next time you see a faint red speck or a razor-white gleam, remember you're reading a thermometer written in starlight, a cosmic code humanity has learned to decipher. Low-mass stars burn fuel slowly and efficiently. Stars span a vast mass range, and the lightest live the longest. Low-mass stars sip hydrogen, turning it into helium with impressive efficiency. Unlike massive stars that exhaust their fuel in a few million years, these small suns can shine for trillions without wearing out. Because they're cooler, they're dim and often invisible to the naked eye. Yet they dominate a galaxy's stellar population. These stars rarely die in dramatic explosions. Instead, they fade into white dwarfs, a gentle ending. Their longevity and stability make them compelling targets in the search for habitable worlds. Though unimpressive in brightness, low-mass stars are patient timekeepers, shining long after the showier stars have burned out. Heavy elements like carbon and oxygen are forged in stars. The universe began with only the simplest elements, hydrogen, helium, and a trace of lithium. Everything heavier, carbon, oxygen, nitrogen, silicon, iron, and beyond, was made inside stars. In their cores, fusion combines lighter atoms into heavier ones, building the chemistry of life atom by atom. When stars die, they scatter these elements into space, where they become part of new stars, planets, and living things. The oxygen in your lungs, the carbon in your cells were born in stellar furnaces billions of years ago. Without stars, there would be no rocks, no oceans, no DNA. Every element heavier than helium carries the signature of a star that once lived and died before us. To study the periodic table is to read a history of starlight, a history written into the matter of everything that exists. Some stars survive near-death encounters with black holes. When a star skims close to a black hole, the meeting can be catastrophic. Tidal forces stretch it, and often it's torn apart. But sometimes, against expectations, it survives. In such grazes, the black hole strips away only the outer layers. The remainder keeps orbiting, battered but intact, often distorted or unstable. Astronomers call these survivors zombie stars, bearing scars of near destruction, yet still shining. Each pass can peel away more material, slowly feeding the black hole and prolonging the star's drawn-out demise. These bizarre systems are natural laboratories for extreme gravity, exposing the thin boundary between survival and destruction. Picture a star limping away from a black hole, its light flickering but alive. You can feel the universe's delicate balance between ruin and resilience. Black holes can steal entire stars from galaxies. Galaxies are crowded with stars, but they don't always stay put. When two galaxies interact, their central black holes can tug of war, snatching stars from each other. On the outskirts, stars can also be stripped as galaxies brush past, drawn toward the core of the rival with the stronger pull. Astronomers have even seen stars wandering between galaxies, likely victims of such collisions. The result is that black holes, along with their host galaxies, act like cosmic thieves, gathering and redistributing starlight across intergalactic space. This large-scale heist reminds us that galaxies aren't isolated islands, but interacting, evolving structures. The stars we see tonight don't remain loyal to their birthplace forever. They're governed by larger forces, changing allegiance when gravity demands it. Star clusters can sink into galactic centers and feed black holes. Galaxies are not static. They evolve, and gravity constantly reshuffles structure. Dense star clusters orbiting near the center can slowly spiral inward over billions of years. On the way down, stars are stripped or swallowed by the central black hole. In this way, black holes grow not just one star at a time, but by devouring entire clusters. Observations suggest some supermassive black holes gained a significant fraction of their mass from these slow banquets. The process also helps explain why galactic cores are often rich in ancient stars survivors of such inward migrations. Imagine an entire cluster gradually sinking into darkness. You can see a galaxy recycling itself with the black hole as the engine behind the changes. Destructive though it seems, this process helps set the delicate balance between light and shadow at galactic centers. When a star wanders too close to a black hole, it can be torn apart in a tidal disruption event. Not swallowed all at once, its material is stretched into a long, glowing stream, wrapping around the black hole and slowly spiraling inward to form a disk heated to millions of degrees. The spectacle can outshine the host galaxy for months or even years. From Earth, these appear as sudden flares, cosmic lighthouses marking a colossal act of destruction. Each star, unraveled into threads by gravity, reminds us that even suns are fragile. Those ghostly arcs of starlight curving through space like ribbons are heartbreakingly beautiful. Though often cast as destroyers, black holes can sometimes act as midwives. As matter falls in some black holes, launch powerful jets that lance across a galaxy. These jets compress gas clouds, sometimes triggering the collapse needed for new stars to ignite. In that way, black holes both destroy and foster creation, regulating the pace of star birth. Many star-forming regions are tied to black hole activity, and their influence can extend tens of thousands of light years, shaping stellar life cycles far away. It's a strange, lovely paradox. The darkest objects in the universe can sow new light. Not every star near a black hole is doomed. Some find stable orbits at a safe distance, close enough to be tightly bound by gravity, but far enough to avoid destruction. Even in the Milky Way, astronomers have tracked stars like S2 and S47111, S47414, orbiting Sagittarius A, the supermassive black hole at the center. They race along at astonishing speeds, some exceeding 7,000 km/s, tracing elegant ellipses that confirm relativity. Watching those orbits is seeing gravity in its purest form, stars dancing around a well with infinite pull. Though they live in a perilous neighborhood, they endure. Their paths are written into the deep wells of space-time. Not every star near a black hole is a tragedy. Some spend entire lives as companions to cosmic darkness. When stars are very young, they're often encircled by swirling disks of gas and dust. Inside, material clumps collide and stick, birthing the seeds of planets. Over millions of years, a whole planetary system emerges, sculpted by gravity and the central star's influence. Telescopes have imaged such disks, revealing dark gaps carved by forming planets, direct evidence that creation is underway before our eyes. Our solar system began in such a disk about 4.5 billion years ago. Stars and planets are born together, their fates intertwined from the start. Studying those disks, is a glimpse into the origin of worlds, a reminder that the planets we walk on and the moons that circle them are the natural continuation of the same process that makes stars shine. The most massive stars pour out radiation and stellar wind so intense that they hollow out their surroundings. These bubbles span tens of light years, their rims glowing with ionized gas. Inside, fierce radiation sweeps material away, leaving a cavity around the star. When many massive stars form together, their bubbles merge into overarching superbubbles, reshaping entire swaths of a galaxy. These structures aren't just beautiful, they influence the next generation of star formation by compressing gas along their edges. From Earth, we see them as luminous shells in nebulae, cosmic balloons inflated by a giant's breath. Some stars flicker because of surrounding dust. When a star dims and brightens irregularly, the culprit isn't always the star itself. Sometimes dust or debris orbiting nearby briefly blocks its light as it passes in front. Tabby's star is a famous example. Its odd dimming patterns puzzled astronomers, and the likely answer lies in clouds of dust or drifting debris. These flickers remind us that the universe isn't an empty stage, but full of material that can obscure, scatter, or filter starlight. To a distant observer, even our sun might blink similarly if viewed through the dusty plane of the solar system. What looks like a solitary point of light is often a hidden family turning together in a long, graceful waltz. The death of one star can spark the birth of many others. When a massive star ends as a supernova, it doesn't simply vanish, it reshapes its surroundings. The explosion sends shock waves into nearby clouds of gas and dust, compressing them and triggering waves of new star formation. In this way, the death of one star can ignite the birth of many more. Our sun may have been born from such an event in a nebula enriched by heavy elements cast off by earlier giants. These cycles keep galaxies fertile with starlight, continually recycling matter into new forms. Each brilliant star leaves more than ashes. It leaves seeds for future suns, planets, and perhaps life. Stars don't simply end. They pass the torch, kindling the next chapters in the universe's unfolding story. A few stars explode multiple times in rare, repeating supernovae. We learn humility as sky watchers. What we see is always shaped by the space between us and the source. Hot, massive stars can sculpt entire nebulae with radiation. They blast intense ultraviolet light, ionizing huge regions around them and making entire nebulae glow. The Orion Nebula dazzles because a central cluster of young massive stars floods the region with energy. Their radiation drives gas outward, carving cavities and creating the delicate light-dark filaments we see in telescope images. Over time, that same energy thins out the very material that formed those stars, halting further star birth nearby. Thus, stars are both creators and destroyers, illuminating the nursery even as they consume it. These radiant sculptures show that light itself wields force, shaping galactic architecture across hundreds of light years. Most stars live in galaxies, great families bound by gravity, but not all remain at home. Some are hurled out by violent events, like close black hole encounters or galaxy-galaxy collisions. These wandering stars drift alone through intergalactic space, far from any shelter, traveling at hundreds of km, isolated for billions of years. Their light crosses unimaginable distances, rarely brushing another stellar system. The idea of a lone sun moving through the void between galaxies is haunting a reminder that even stars can be exiled, still shining in defiance of the vast, quiet dark. The atoms in your body were forged long before you were born, deep inside stars. Nuclear fusion turns hydrogen into helium, then helium into carbon, oxygen, and nitrogen. Massive stars go further, creating silicon, iron, and many other elements. When they die, they scatter those elements into space, enriching future generations of stars and planets. Every breath of oxygen you inhale, every carbon molecule in your cells, every trace of iron in your blood, all were once starlight. Stars are alchemists on a cosmic scale, smelting simple gas into the building blocks of life. Looking up at the night sky is reading your own origin story, written in blazing furnaces, billions of kilometers away. We are quite literally stardust, carried forward into consciousness. At their cores, stars are colossal fusion engines. Gravity squeezes hydrogen atoms so tightly that they fuse into helium, releasing energy as light and heat. That process, nuclear fusion, is the reaction humanity hopes to recreate on Earth as a near-limitless energy source. The balance between inward pulling gravity and outward pressure from fusion keeps a star stable for billions of years. Without fusion, a star would collapse under its own weight. Thanks to fusion, it shines across unimaginable distances, nourishing galaxies and bringing life to planets. Every twinkle is the direct light of fusion atoms joining in a steady flame that turns the universe's raw matter into radiance. Hydrogen. The simplest and most abundant element is the raw fuel of most stars. In the core, the pressure is so great that hydrogen atoms slam together and fuse into helium, releasing bursts of energy. Over time, helium builds up, altering the star's internal balance and eventually making it expand, contract, or enter new phases of stellar life. In massive stars, fusion proceeds further, creating ever heavier elements, but it all begins with hydrogen. Every sunrise is the immediate result of that quiet, persistent transformation, a chain of reactions that has burned for billions of years and will continue far into the future. The light, warmth, and chemistry of the cosmos all trace back to hydrogen being squeezed into helium, one fusion reaction at a time. Stars don't last forever, but their deaths aren't an ending. When they go supernova or shed their outer layers, stars enrich their surroundings with heavy elements. That gas blends into the interstellar medium, becoming dense clouds. Over time, gravity pulls those clouds into collapse again, igniting new stars. Each generation carries the legacy of the one before, building more complex chemistry with every cycle. Our sun was born from the ashes of older stars, carrying elements forged in ancient explosions. One day, future stars will rise from the remnants of our sun, continuing the chain. It's a cycle of birth, death, rebirth that keeps galaxies from ever standing still. Stars live, stars die, and stars are reborn, stitching time together with countless transformations. Not all galaxies form stars at the same pace. In starburst galaxies, harsh conditions make stars appear hundreds of times faster than in the Milky Way. Galaxy collisions often spark these bursts, compressing gas clouds into waves of intense star formation. Entire regions blaze with young massive stars. Their radiation floods space with energy. These galaxies glow in infrared, revealing the heat of countless newborn suns. But the fever doesn't last. After a few 100 million years, the gas is used up or blown away, and the starburst subsides, leaving a galaxy permanently marked by that brief chaotic phase. Not every star is born alone. Some begin life among dozens of close siblings. Our sun likely formed in a cluster, surrounded by many brothers and sisters. For some stars, the crowding is even more intense in a stellar nursery. Dozens or even hundreds of stars ignite close together with gravity tugging and twisting their orbits. Some systems become bound multiples. Others scatter their siblings over time. Being born in a crowded neighborhood means dramatic interactions, stealing one another's planets, flinging companions away, or disrupting growth. Yet that's also where the richest chemistry unfolds. Shock waves, radiation, and stellar winds churning the material together. Imagine a star's earliest moments, not as solitude, but as a noisy, radiant daycare. Dozens of suns lighting up side by side, competing and cooperating at their dawn. When sun-like stars run out of fuel, they contract into white dwarfs. Though they no longer burn by fusion, these remnants stay hot and luminous from stored heat. Over billions of years, they slowly cool and fade. The time scale is so vast that the universe isn't yet old enough for any white dwarf to have gone completely dark. Even dead stars still shine their faint glow, marking the quiet graves of suns that once blazed. By studying them, we can measure the ages of star clusters and trace a galaxy's history. To see a white dwarf is to see both an ending and endurance, the afterlife of a star still quietly shining after a fiery youth. Not every star is born in a small family. Some live in enormous clusters. Globular clusters, for example, cram hundreds of thousands to millions of stars into tight spherical swarms, orbiting their galaxies like stalwart satellites for billions of years. These ancient groups harbor some of the oldest stars in the universe, relics of an earlier cosmic era. Stand inside one, and the night would be impossibly bright, thousands of suns on every horizon. Studying such clusters reveals stellar evolution, galactic history, and the limits of gravitational binding. They are natural laboratories where stars coexist at extreme densities, letting us see what a community of stars looks like at the edge of possibility. Picture standing on a planet within such a cluster, the sky ablaze with countless lights. Some stars are kicked out like runaways when a cluster blows apart. In crowded clusters, chaos rules. Stars tug one another askew, and when one goes supernova, it can wreck the gravitational balance. Sometimes that turmoil slings stars outward at tremendous speeds, creating runaway stars that streak across a galaxy. They can reach hundreds of km/s, charting lonely paths far from their birthplaces. Astronomers identify them by their motion, often seen racing away from clusters or supernova remnants. Runaways tell stories of violent beginnings, the gravitational dice rolls that sealed their fate. Exiled from their bustling homes, they carry the memory of explosive origins, their speed a living testament to the forces that hurled them away. Some stars in the Milky Way orbit Sagittarius A, the black hole at the center. At our galaxy's heart lies Sagittarius A, a supermassive black hole about 4 million times the Sun's mass. Astonishingly, some stars orbit it directly. Astronomers have tracked them for decades, watching them complete long loops around the invisible giant. One star, S2, passes so close that it whips around the black hole at over 7,000 km/s. Observing these orbits has given us some of the clearest evidence for Einstein's general relativity, with starlight bending and redshifting exactly as predicted. These stars live in a perilous neighborhood, yet endure blazing defiantly as they dance around a gravitational abyss. To watch them is to watch the cosmic waltz at its most extreme, suns twirling at the brink of darkness. Black holes don't just swallow stars, they warp the space around them. Stars trapped nearby often move along oddly twisted paths. Some are slingshotted around at dizzying speeds. Others spiral inward to destruction. Even stars at safer distances feel space-time's curvature, tracing paths that veer from Newton's predictions. Tracking these motions gives us a natural lab to test physics' limits. In the Milky Way's core, those bent orbits lay bare Sagittarius A's raw power without ever seeing it directly. Although most stellar explosions are final, there are exceptions. In extremely rare cases, a massive star can erupt violently, survive, and then explode again years or decades later. These events are called pulsational pair instability supernovae. The star becomes unstable, ejects enormous amounts of mass, then temporarily stabilizes, only to later collapse for good. Such stars brighten erratically, producing multiple dazzling flares that can make astronomers think they're witnessing several supernovae in the same place. These unusual deaths reveal how diverse massive star fates can be, and how much we still have to learn about the limits and instabilities of nuclear fusion. In a cosmic sense, these are stars that refuse to let go, leaving a dramatic flickering record of their final struggle with gravity. Type Ia supernovae help us measure the size of the universe. Type Ia supernovae are a special class of stellar explosions that shine with remarkably consistent brightness. In distant galaxies, tightly wound stellar streams also confirm supermassive black holes too dim to view. The way stars' paths curve is both a map and a signature, the hidden fingerprint of gravity at its most intense. The nearest star beyond the Sun is still more than 4 light-years away. The Sun feels close and familiar, but its next neighbor is unimaginably far. Proxima Centauri, part of the Alpha Centauri system, sits over 4 light-years away, about 40 trillion kilometers. If a spacecraft flew as fast as New Horizons, which has left the solar system, the trip would take nearly 80,000 years. Yet by cosmic standards, Proxima is still our closest neighbor, and it even hosts at least one planet in the habitable zone. Look up at the night sky and realize even our nearest stellar friend is separated by a gulf so vast that light itself needs years to cross it. That perspective makes the Sun both more precious and less special. Just one star among many, but the one that sustains our fragile existence. The Sun is only one of the Milky Way's hundreds of billions of stars. It may dominate our sky, but it's just part of a colossal stellar disk. Every one of those stars has its own story, some solitary, some paired, some with planets, some ending in violent explosions. That sheer number means that for every star we know, there are billions more quietly burning along the galaxy's spiral arms. Many are smaller red dwarfs, glowing dimly for trillions of years. Others are giants, shining thousands of times brighter than the Sun. From Earth, even on the darkest nights, we see only a tiny fraction of them. To imagine the Milky Way in full is to picture a glowing disk so vast that our Sun is a single grain within its sweep. Our star is both ordinary and extraordinary, a common light, and the light that made our world. Almost all the stars you see at night belong to the Milky Way. On a clear night, nearly every point of light is local part of our own galaxy, our stellar neighborhood scattered along the spiral arms. Only a handful of bright smudges like the Andromeda Galaxy come from beyond. The Orion's Belt, the Pleiades, the stars of the Big Dipper. They're all family, cosmically speaking. The Milky Way is so dense with stars that where skies are truly dark, it appears as a luminous band, the combined light of millions of suns. What feels like a private glittering dome is really a cross-section of a vast spinning disk. Remembering that helps us feel both small and connected. The night sky isn't random, but a window into our galactic home. Stars can be torn from their galaxies by gravitational encounters. Galaxies aren't static. When they collide or pass close by, their gravity tugs at everything within. Stars, once securely bound, can be hurled into intergalactic space. These intergalactic wanderers drift alone, belonging to no galaxy, carrying their light across the void. Some even bring along planets' worlds, without a home, traveling together through emptiness. Such exiles can roam for billions of years, never returning to a galactic roof. Observations show that intergalactic space isn't truly empty, but peppered with such wandering stars. Each one reminds us that galaxies are living, moving structures. The ties binding stars can, under the right conditions, be snapped by gravity's persistent pull. Stars can leave behind planetary nebulae like cosmic headstones. As sun-like stars near their end, they swell into red giants and shed their outer layers. Those layers drift into space, forming glowing shells lit by the remaining core. The result is a planetary nebula, a misleading name, but a gorgeous structure, unrelated to planets. In truth, these nebulae are luminous memorials announcing a star's departure. They can persist for tens of thousands of years, sketching delicate shapes and colors across the sky before fading into interstellar dust. Famous examples like the Ring Nebula or the Helix Nebula hint at what may await our sun in a few billion years. Even as they mark an ending, planetary nebulae seed space with fresh material, ensuring creation continues. White dwarfs are the cooling embers of stars. When stars like the sun die, they contract into white dwarfs, Earth-sized, ultra-dense remnants that no longer fuse but still shine from leftover heat. A teaspoon of white dwarf material on Earth would weigh tons, evidence of the crushing pressure that holds it together. Over time, they cool and fade, eventually becoming black dwarfs, though the universe is still too young for any to exist. White dwarfs are astronomical fossils, preserving clues about the ages and histories of galaxies. To see one is to glimpse both an ending and a quiet persistence, the final echo of a star that once burned bright. Some stars die gently, others in a storm of fire. Not every star shares the same fate. Small stars like red dwarfs dim and cool into white dwarfs with little drama. Massive stars, by contrast, often end in violent supernovae, blasting their outer layers into space in spectacular displays of light and energy. Those cataclysms forge and disperse heavy elements, enriching galaxies with the raw materials for planets and life. The most massive cores can collapse into neutron stars or black holes, leaving behind some of the strangest objects in the universe. The diversity of stellar endings mirrors the diversity of stellar lives. Quiet or cataclysmic, every finale feeds the cycles that keep galaxies evolving. A star's death is never just a period, it's the start of something new. Stars remind us that the universe is always changing. Looking up at the night sky, you see both eternity and impermanence. Stars seem fixed constellations, unchanging. Yet over time, stars are born, live and die, constantly reweaving the sky's tapestry. Nebulae blossom where new stars flare to life. Supernovae blaze where old stars collapse. Clusters disperse, galaxies collide, and wanderers drift into the dark. Even our sun is only temporary. One day it will swell and fade. Stars remind us the cosmos isn't still, but alive with change. Every sparkle is a moment in a story, billions of years long. To see them is to glimpse both the everlasting and the inflowing. The universe's slow, expansive heartbeat carries us forward in its endless rhythm. Thank you for taking this quiet walk among the stars with Easy Sleep Science Channel. We've traveled from fiery births in vast clouds through steady lives to silent embers and explosive ends. Along the way, we've seen that stars aren't just distant points of light, but the architects of everything we know, makers of atoms, keepers of time, storytellers for the cosmos. It's humbling to think the blood in your veins, the air in your lungs, the bones in your body were forged in the hearts of ancient suns. Stars lived, died, and scattered their ashes so that one day you could be here breathing softly beneath their glow. The night sky isn't simply a show, it's a creation history written across space. As we close this tale, you don't need to hold on to every detail. Let them drift like stardust on the breeze. What matters is the feeling, the vast, quiet peace, the sense of being both small and deeply connected. You are part of this universe woven from the same stuff as the stars. If you found calm here, I'm grateful if you'd consider liking, subscribing, or leaving a note in the comments. It helps others find the channel one sleepy soul at a time. But for now, you don't have to do anything. Just let your breath slow, let your body soften, and feel the weight of the day slip away. The stars will keep burning. The galaxies will keep turning, and you can simply rest. Somewhere out there, a star is shining with light that won't reach Earth for thousands of years. By the time it arrives, you'll have dreamed 1,000 dreams, and the world will have turned countless times. Stars remind us that time is both vast and gentle, a current we can surrender to. So let yourself drift, carried by that flow, into the quiet of the night. Sleep well, dream deep, and know that the starlight blanketing the sky is also within you. Good night.